Alrighty, so now let's talk about a hypothesis test for a matched pairs design, or more specifically, a paired t-test. Now, I didn't include any template in here because it is extremely identical to a one sample t-test. The only difference is now that we look at mu d, and no, that's literally it. We use x bar d and sd instead of x bar and s. Well, confidence intervals are used to estimate the population parameter, and from previous lessons, we were estimating the mean difference, and otherwise known as the average difference for a matched pairs design. With hypothesis testing, we are aiming to evaluate if there is any significant evidence that would claim that there is no difference in the pairs. Thus, we assume the null hypothesis that there is no difference between the two, that mu d equals 0. Now, an example here is that makers of a new pain-relieving medication claim that it relieves chronic pain faster than the current top-selling pain reliever on the market. A double-blind experiment was conducted in which 10 people who experienced chronic pain were randomly selected to take either the new or the current medication. Each of the 10 people recorded the time in minutes from taking the medication until pain relief. And after an appropriate time period, each of the 10 people took the other medication and recorded the time in taking the medication until pain relief. Now, the medication each person took was randomly determined, and because both medications looked the same, the people in the study did not know which medication was taken first. The table below shows summary statistics for the results, and we're told that a dot plot of the results reveals no extreme skewness or outliers. Is there significant evidence to claim the new medication is effective in lowering the average time until a person experiences pain relief? Now, there's a lot going on there, but here I have my new medication and my current medication. So I have the elements of comparison. I've got random assignment. I have control, and we have replication. We're using 10 people. Well, the difference here is defined for us as new minus current. So I want to see, does the new medication have a lower average than the current medication? Well, since we've already been defined as n minus c, we're going to define this by moving the c to the other side. So we are now testing that n minus c is less than 0. We're testing that mu d is less than 0. So in my state component, I want to test the null hypothesis that the mean difference is 0 against the alternative that the mean difference is less than 0, where mu d is the true mean difference in pain relief time. In my plan step, I have my sample size of 10, my average of the differences, and my standard deviation of the differences. Now, here in our plan step, since this is an experiment, instead of checking that I have a random sample, I was told that 10 people were randomly assigned that they were either going to take the order of their medication. It was randomly determined, it was randomly assigned. Now, normally when I have experiments, I do not check the 10% or the independent condition because of those control groups, these control and treatment groups. Of course, the results are independent. They have two separate treatments. And typically I use volunteers in an experiment. But here, this is now where, again, we have to read. Since they were randomly selected, I have a random sample. That means I do have to check the 10% condition. So 10 people is less than or equal to 10% of all people who experience chronic pain. Now I put this with stars around it because you don't have to do this every time you have an experiment. This is just a special case where I have a random selection of participants for my experiment. Now on the AP exam, if you accidentally check the 10% condition while it's clearly an experiment, you are going to get penalized and they will deduct your score. So that'll take you from a 4 to a 3 or a 3 to a 2. Because this shows that you are not understanding when you use each condition. This just shows that you've memorized templates. So I put stars around this one because this is, again, is a special case where we randomly selected volunteers for our study. Now, the normal model here is appropriate since the sample data appears approximately symmetric by this sentence here. Now, since these conditions are met, I am going to use a paired t-test for a population mean difference. I'll start by computing my degrees of freedom. So 10 minus 1 gives me 9. And now I have my test statistic here. Again, the statistic minus the parameter over the standard error. And again, mu d we assume is 0. So I get a test statistic of about negative 0.9634. So to find the p-value, since I was told that in my alternative I'm checking a less than, I'm going to use this t model. So I'll go here to my calculator. And again, we're going to start on the Calculate tab. We are going to go to Menu. We're going to go to Statistics, and we will go to Distributions. Here I want a TCDF function, so I want some very large negative number, so just put a bunch of 9s. My upper bound is what we obtained, which was 0.9634 and a negative. That will change everything. So negative 0.9634, and I have 9 degrees of freedom. So I do this, and I get a large p-value of about 0.1803, or you can copy all of that if you want to. I'm not going to tell you how to live your life, but I would make it simpler by just doing this 0.1803. So again, what we do here is right here. We're assuming a normal-ish model, and we're using a t-distribution because we don't know the population standard deviation, right? This t-distribution accounts for this extra variation in the sample. And what we're doing here is our normal model is appropriate-ish because our sample display revealed no extreme skewness or outliers, so it's reasonable to assume it might have come from a normal population or that the sampling distribution is approximately normal. So I formed this normal curve, and my standardized test statistic of negative 0.9634, I'm testing a less than, so I want to find the probability of obtaining my sample mean difference or something more extreme. That comes out to about an 18% probability. That's not statistically significant. About 18% of the time, we'd expect this result to happen. There's nothing special here. So what's going to happen is that since my p-value of 0.1803 is greater than my significance level of 0.05, and let's see, were we told anything? Nope, we were just told to run the test. So since my p-value, since the p is greater than the alpha, we fail to reject the null hypothesis, and we fail to reject because there is not sufficient evidence to claim the new medication lowers the average time until pain relief when compared to the current medication. Now, a follow-up question to this could be, describe the error. Well, we failed to reject the null, so this could be a type 2 error. Or maybe, had there been a statistically significant result, could we conclude the new medication lowers pain relief time quicker than the current? Well, we could because of the random assignment, but here we did not obtain a statistically significant result, so this won't be any kind of special for us. Now, another thing could be, what could explain this result? And I just want you to think about this. 10 people is not a lot. This is a very small sample size, so anything significant with these 10 people could probably only be generalized to the population from which these 10 people were randomly selected. Or if we would have used volunteers, there could be a potential hidden confounding variable. And you got to think through this thing, like what else could have happened? Also, look at the way we collected the data. We took both medications within a reasonably close time to one another. We just take one, we wait some time, and then we take the other. What if the first pill that I took was actually effective, and then that's confounded with me taking the second pill almost immediately after? So there's kind of there's some good stuff in this design. It meets our components and conditions, but also the way we do it could possibly be improved. So typically on the AP exam, you'll get to do your hypothesis test, but there's typically always a part B. There's a what if question. There's a extend your concepts, extend your understanding. So just be prepared to do that. Well, I want you to go ahead and try this one out. And I gave you the answer here to the first one. But go ahead and pause the video and give yourself about 5 to 7 minutes to try out this example. All right, so looking at our water diets, again, the issue of small sample sizes. So what type of study is being described? Well, there was no random assignment, so I'm going to have an observational study. And this is an observational study using a matched pairs design. Notice there was no random assignment. Each volunteer served as their own control, and I was doing a before and after study. So this is pretty indicative of a matched pairs design. What is one potential confounding variable? Well, what about lifestyle? What about your genetics? What about your gender identity? What about the fact that you are choosing to be a part of this study? Right? There's a lot of variation that can happen here, and we're not sure if that's due to the diet or due to one of these other variables, but we're not sure whether it's the diet or one of these confounding variables that has the most influence on weight loss. Next up, if I were testing that my after weight is less than my before weight, that I actually lost some weight here, if I were to define the difference as before minus after, which I believe it was defined for us in the problem, we would set up this set of hypotheses. We are testing that there is a positive mean difference. Now, if we obtained a statistically significant result, could we conclude that the diet is effective in weight loss? Again, another favorite on the AP exam. Statistically significant results from observational studies are not convincing. And that's because we did not use random assignment. I'm not balancing out the effects of confounding variables. So again, I'm not sure, is it the diet or is it one of these confounding variables that is leading towards this significant weight loss? But again, if you have a significant result from an observational study or a survey or a sample, no bueno, because correlation does not equal causation. What we need is that random assignment in order to infer cause and effect. Now, a two-tailed test is performed and we get a p-value of 0.38. Now, what would be this p-value if it would have been one-sided? Well, let's look here. It's like we're doing this here. We assume the truth is here at 0, and two-sided would mean I'm looking at two tails. And here, since we're looking at a positive mean difference, I'd only want the right side of the tail. So 2 times the p-value would give me 0.38. So here, that's my two-sided, I just want one of these sides, I'll divide by 2. So my p-value would be about 0.19. Remember, in a two-tailed test, we're just looking that there is some difference. And in a two-tailed test, we're saying that we don't know if the difference is positive or negative, but we know there is some difference. Thus, we're testing the alternative that the population mean difference is different from 0 or not equal to 0. So that's going to conclude our time here with paired t procedures. So we learned about the paired t interval and the paired t test. And again, we were looking at one sample of the differences. So in the next 2 lessons that follow, we are now going to look at 2 independent samples from 2 separate populations instead of 2 samples on 1 population of the differences. So stay tuned to learn about 2 sample t procedures.